Welcome back. So now let's do an example of related rates. We've seen the 6-step process, which probably doesn't make a lot of sense right now. You can't picture what's going on. But as we go through the example, and I'm just going to do one example today, and then I'll do 4 examples tomorrow. I'll emphasize the process, each of the different steps and what's going on, and we'll look at some classic examples of related rates. You should have received the packet and on related rates. If you haven't got the packet yet, go ahead and pause the video and hand out the packet. Make sure that everybody's got it. You should have problems A, B, C, D, and E. We're going to do A today, B and C tomorrow in one video, and D and E in the second video tomorrow. All right, so here we go. So our first related rates problem. Diagram's not so good. I've made copies of this so many times. So it says, assume that oil spilled from a ruptured tanker spreads in a circular pattern, whose radius is increasing at a constant rate of 2 feet per second. How fast is the area of the spill increasing when the radius is 60 feet? So you can picture this. The radius is getting bigger, 2 feet every second. 2 feet, 2 feet, 2 feet, 2 feet. Well, the area is getting bigger as well. I've got 2 different rates here. The rate of change of the radius and the rate of change of the area. So step 1, let's draw a picture and name the variables and the constants. I think this is a pretty good picture. I've got a circle and I've got a radius. My constants are the radius is increasing at the rate of 2 feet per second, and I want to know how fast is the area increasing, the rate of change of the area increasing when the radius is 60 feet. So now we're going to write down all the numerical information in terms of the symbols we've chosen. Well, we know we've got the radius. What is this 2 feet per second here? The radius is increasing at the constant rate. This is rate of change of the radius, dr dt. And dr dt is 2 feet per second. And when the radius is 60 feet, when the radius is 60, I want to find the rate of change of the area, dA dt. So write down what we're asked to find. There it is. There's the rate. That's what we're trying to find. The rate of change of the area over time when the radius is 60. All right, so now we need an equation, step 4, we need an equation that relates all of these variables. And we really only got 2 variables, area and radius. And of course, it's going to be the formula for the area of a circle. Area equals pi r squared. So here I've got my radius and my area. These are all the variables that I need. So now we're going to take this and we're going to differentiate with respect to time. So d dt of the formula area equals pi r squared. All right, so the derivative with respect to time of the area is dA dt equals, pi is a constant, remember. I could pull that pi out here. So pi times, and then the derivative of r squared is going to be 2r dr dt. Implicit differentiation, the derivative of the area with respect to time, dA dt. Pi, constant, pull it out. The derivative of the radius squared with respect to time is 2r dr dt. And what I'm trying to find is dA dt, so the next step would be to solve it in terms of what I'm trying to find. Notice that's already done for me here. I know dA dt. So now the last step, step 6, evaluate using all the known variables to find the rate. So I know I want to find the dA dt, the rate of change of the area, when the radius is 60 and the rate of change of the radius over time is 2. So I'm going to plug in the 60 here and the 2 there. And the rate of change of the area over time is pi times 2 when the radius is 60 and the changing rate is 2 of the radius. So multiply all this together. 2 times 60, 120, 240 pi is my dA dt. And it's interesting, it's worthwhile looking at what exactly are the units here. This is the change in area over time. Area is square feet per second. So the change in the area when the radius is 60 is 240 pi square feet per second. That's how the area of the oil spill is changing as a function of time. All right, so this one wasn't so bad, finding the equation, but let's just take another look at this and kind of talk about all the different steps that we went through here. So step 1, drawing a picture, naming all the variables. I think that was done for us. Step 2, writing down all the numerical information. Step 3, what are we asked to find? Find an equation. Step 4, that relates all these things together. Differentiate with respect to time. And then what we get, we want to solve for what we're trying to find. And this one was already done for us. And then evaluating, substituting in. So this one wasn't so bad. This is a nicer, kinder, gentler one. Is it always going to be that easy? Well, no, of course not. We'll get into ones that are much more difficult. All sorts of crazy stuff going on here in a moment. But this seems like a good place to start. So this is it for today. I hope again, I hope the quiz went well. I will grade those at home and enter the grades and get it back to you so you can see. And tomorrow we'll really get into it. If you go home, take a look at the homework tonight. Look at it, see what you can do with it, see if you can figure any of it out. I think that some of these you'll be able to do, and then some of them require tricks, like the cone. We're going to see lots of cones. Cones are a special case here. All right, well, good luck, and I will talk to you tomorrow.